So the problem that I worked on, which we use the deep genetic or CNN architecture, is essentially the intracranial aneurysm, which is basically what we wanted to do is we wanted to take the 3D BSA images and we want to use deep convolutional neural network to automatically segment the vasculature that is surrounding this iris, right? So that's what we want to do. So let me explain this problem, what we worked on that. So what are this? The cerebral aneurysms are essentially, this bulging spot that you find, which are definitely happening in your cerebral vessels. And what happens is, like, if this ruptures, then there is a typically that leads to high mortality and morbidity, right? But typically the rupture risk is low, and the treatments has also risk. So you need to analyze this, 3D BSA images in order for you to, take this diagnostic approach that what should be the next step? Shall we treat it, or what are the next options? So in order for you to do that, this is a very manual process. So what you typically done is, like, from a BSA image, the person who will be there, he will be cleaning up and he will be basically creating this sort of images that you are having, and then you can recognize some of the morphological features of this, bulge that we have. For example, the room height, neck diameter, and they can be essentially an indicator of, the treatment option that you might want to follow after you have detected this BSA image that you get. Now the challenge is, like, when you get, the overall images that you have, typically the overall image is like, this BSA image is very, very complex, and you really want to focus on this aspect. So from a very complex BSA image, what you want to do is you want to get a small region and you want to basically get this clean copy. This right now is a manual process, and somebody does it manually, and it's a very, very tedious process that we did. So we wanted to automate a pipeline from full-scale BSA image. We want to basically get this vasculature image, which is clean, and now we can do this calculation easily on that segmented image that we have. Okay, so the overall calculation pipeline that we built is, like, we had, patient-specific 3D BSA at the University of Buffalo Medical School, which we basically processed, and we created the segmented surfaces. We did manual processing, we cleaned and smoothed manually, and this helped us in basically, when we use MATLAB code, like, to develop a rock slide representation. So all of what you see here on the top line is essentially what helped us in creating data that goes into feeding the CNN. And the CNN model that we use, there are different CNN model, unit and deep predict, but essentially deep predict gave us a really good performance, so essentially we proceeded with that, right? So this is how we created the training data. And then, what we did for the online prediction, when we get a new patient-specific BSA, we essentially use the CNN model that we have trained to get the probability maps. And from this probability map, essentially this helps us in cleaning up that image that we have. Okay, so from there, we basically do some thresholding and we get this, segmented results that we have. So I want to talk about two main components that we have done as a part of this. So what you typically have as an input is you will have this patient-specific 3D BSA image. Okay? So what we do is, like, the vasculature that we are interested in identifying is a small region of this whole image. So one of the steps that we do is we do what is known as automated localization, which is, rather than taking everything that is there in the BSA image, can we quickly zoom on the important region and find that important region. So we trained a neural network which essentially identifies this localized location, or this cube where aneurysms are present, and so we want to focus there. So that was step one, and then from there we basically created a segmentation algorithm which takes this portion, cube of volume of information that is there, and it automatically creates this figure for us. Okay, so here are some of the examples that you can see from training of the neural networks that we had. So this is the blue that you see here is essentially the true level, and the green that you see is essentially coming up from the architecture that we have. So you can see that localized location where the aneurysms are there, we are able to identify that very, very clearly. Okay, and the second aspect that we did is essentially we also, as I said, we did a lot of testing, but essentially what we want to do is we want to identify clean, and this is the output of the CNN, which is the clean vasculature that we want. And once we have this, then we can provide this to a doctor, and he can basically use this image to prescribe what should be the next treatment steps that you have. Now, So a couple of things that I want to mention is like, pre-processing of data is there, but we also did what is known as post-processing. Because one of the issues or artifacts of CNN is like, on top of this clean images, there will be some disconnected parts and other things that will come as an outline or output of the CNN that we have. So we used some classical techniques from computer vision, which is known as morphological based operations, to clean up these images, and after that morphological operations, you have essentially, these clean images that we get. So on top of pre-processing, there is also some post-processing involved in this application. So with that, I will stop, and I want to thank you for listening to me. And then again, if you're interested in what we've done, this is the reference of the paper that I want to point you to.